Hi, I'm Bianca Coker from Region 10, one of our math consultants here, and I'm going to share with you in this video a little bit of information about one of our new math standards, 7-9D. This is in our expressions, equations, and relationships strand. 7-9D states that the student applies mathematical process standards to represent linear relationships using multiple representations. The student is expected to represent linear relationships using verbal descriptions, tables, graph, and equations that simplify to the form y equals mx plus b. All right, that's a big one. Okay, but it's really not that hard. Let's look at it. First of all, in the first part, we have process standards. Remember our process standards, those 1, A, B, C, D, E, F, Gs. Those really talk about multiple representations. We want our students to be able to communicate mathematically, and we want them to be able to communicate among multiple representations. And that's really a great thing, because when we use multiple representations, whether students are a visual learner or a kinesthetic learner, they can connect to the mathematics. And then what we have them do, besides just picking the one they like the best, is seeing the connections between the multiple representations. And that's very powerful. If a student can see a value in a table and point to it on a graph and show where it happens in the equation and show where it's happening in the physical model, they know it. They know it, they know it. And we want to make sure that our students have mastered these concepts. They're very critical to their future success, both in mathematics, but in school, and I think in life. So, process standards want us communicating, our students communicating mathematics, and we're going to communicate them with multiple representations. And in this standard, we're looking at representing linear relationships with multiple representations. So, let's look at the next piece. The student is expected to represent linear relationships using verbal descriptions, tables, graphs, and equations. Okay, so that part in the pink there, that is the 4 things they're supposed to do. So the first thing I have my students do is take a piece of paper and fold it lengthwise, and or I like hamburger hot dog, right? Hamburger hot dog, so we have 4 sections on their paper. If you're using whiteboards, just put a big cross in the middle and you have 4 sections. Whatever you do, you want to have those 4 sections so that you can represent in one section verbal, one section table, one section graph, and one section the equation. All right? Now, that green part, y equals mx plus b, seems a little intimidating. However, that just means it's a linear equation, a linear function. Y equals mx plus b is that form of an equation that if you can simplify an equation to match that style, where you solve for y and simplify it on the other side, you have x to the first power, you have maybe a coefficient in front of x, and you maybe have a constant term b, then you have a linear equation, a linear function. That's all that's saying. You don't have to do this for quadratics, you don't have to do it for absolute values, exponents. All you have to do it for is linear functions. So it's meant to kind of comfort you. However, maybe that's not happening. All right, so let's look at an example. Here's an example of 3 of the 4 representations. I couldn't fit the graph in on this one. Timmy is running towards a hole in the ground 50 feet away at a rate of 3 feet per second. So this is for you old Lassie fans. Timmy was always getting into trouble. So Timmy's running towards a hole in the ground 50 feet away at a rate of 3 feet per second. So that's our verbal description of our linear function. Now let's look at to the table next. I like doing the table next because we take that verbal and we kind of unpack it into the table. So at time 0, Timmy is still 50 feet from the hole. Yay! After a second, Timmy's run 3 feet closer to the hole. So now he's 47 feet from the hole. Fast forward 5 seconds. Timmy's run 15 feet closer to the hole. He's now 35 feet from the hole. Lassie needs to hurry, right? So that table gives us some values that we can put in our graph. But that table also helps us figure out what our rule is or what our equation is for this situation. Looking at the table, we can find our change in y and our change in x. That'll give us our unit rate or our slope. And then we know our starting point from this table is 50 feet. So we know our rule is 50 minus 3t equals the distance from the hole. So looking at our table second allows us to create our equation for our third section. Or you could have put your graph in next and then done the equation. Totally up to you, totally up to the students what order they do these in, but they need to be able to represent it all four ways. Now let's take those points or that equation and make a graph. Here's our graphical representation. Now, remember what I was saying. We need to be able to connect what we're seeing in each representation to what's happening in the other representations. So going back to our verbal description, where the graph is crossing the vertical axis or the y-axis, that's where Timmy was at time 0, where he was 50 feet from the hole, right? When we look at the rate at which Timmy's running towards the hole at 3 feet per second, and because he's decreasing his distance to the hole, then that line is sloped downward. It has a negative slope. And then it has a slope of 3, negative 3 really, because he's going down 3 feet, or he's going closer to the hole 3 feet every second. So as we go down 3 and we go over 1, we're going to hit that line again if we use our slope triangles. We can also kind of see when Timmy's going to fall into the hole by looking at our x-intercept. So there's a lot we can tell from our graph. Now, if we were to plot our points from our table on this graph, we would see those dots show up at the y-intercept at 1 second, at 5 seconds, I believe. Those are the 3 we had plotted. And we can see those graphs, points on the graph right here from our table. And then our equation, well, when we start talking about our equation, we can see our negative slope in this equation because a line goes down. We can see our starting point, which was at 50 feet. And we can even use a slope triangle to calculate what exactly that slope is. So any of these things can generate those other representations. And we want our students to be able to do that. And we want our students to be able to understand where they're seeing all the different elements and all the different representations all the time. Sounds like a big order. We've got a lot of work cut out for us, but I promise you your students will understand it better if we use our multiple representations. Thank you and have a great day.